Yeah, so in this video, we're going to be covering lead code hard problem number 2577, which is minimum time to visit a cell in a grid. So basically, in this problem, we are given a m cross n matrix grid consisting of non-negative integers, where grid of row column represents the minimum time required to be able to visit the cell row comma column, which means that we can visit the cell row comma column only when the time you visit it is greater than or equal to the value stored in that row and column. So that cell. So you are standing on the top left, which is at 0, grid of 0, 0 in the matrix in the 0th second, and you must move to any adjacent cell in the 4 directions up, down, left, and right. Each move you make takes 1 second. Now what we need to do is we need to return the minimum time that is required for us to visit the bottom right cell, this one. And if in case we are not able to visit it, we return -1. So our aim is to reach this cell, and if we are not able to reach it, we return -1. So for this example, you can see this is the matrix m cross n, and the grid, we have to take the path. So at t equals 0, we are on the cell 0 comma 0. I'll explain you with the help of this annotation. So at t 0, we are here. At t equal to 1, we move to cell 0 comma 1, we move here, because grid of 0 comma 1 is less than or equal to 1, right? So we can visit this. Then we visit at t is equal to 2, we visit this cell 1 1, because the value again is less than equal to 2, right? Because the time is increasing. You see, this is the value of the time, and this keeps on increasing, and these are the iterations that we make on the grid, like wherever we are going. So at t is equal to 1, we moved here. T is equal to 2, we moved here. At t is equal to 3, we would move here, right? Then we see that we cannot move further from this point because the time is 5 or 8, either 5 or 8. So what we can do is that we can move back to the cell as well. So once we move here, then we move here, then we again move here. Since we cannot go in either of these two directions, we would go back here to waste time, which we can do, and then come back to this location. Or either, if not coming back, then we can go down here, right? So once we have done that, grid of 1 3, okay, well, let us see. Grid of 1 comma 3 would be, this is 0, this is 1, and this is 3 here. So we basically went from here to here, then here. So these are 3 seconds gone. Then the 4th second we come back, 5th second we come here, then the 6th second we come here, now because it is value less than 5, less than equal to 6, I mean, and then we can go here. So you see that the time keeps on increasing. What we need to do is we need to make sure that the cell we are visiting, the value in that cell should be either less than or equal to the time that we are at, right? So that's the main aim of this problem, and therefore the final time is 7. That is the minimum time possible. Similarly, in this example, you can see that since there is no 1 here, we cannot be stagnant at any cell and waste time. We have to either move forward, basically to the right, to the left, to up or down. So we cannot be stagnant at a particular cell. So in this case, you can see that at 0, there is no 1 here or here. So it cannot move here or here, and obviously it cannot go out of bounds. So that is why we would return -1, because there's no path from top left to the bottom right, because the time is not less than or equal to the current grid cell, right? So that's about the explanation of the problem, and now we'll get right into the code part. So firstly, this is the main part. Min time is the function. So we are given vector of int of grid, right? And we take the grid size, and the basically m is the grid size of the rows. Number of rows is m, and number of columns is n. Now we check if both the initial moves require greater than 1 second. It is impossible to go forward, as I showed you in the example 2. That in case none of the the grid of 0 comma 1 is equal to 1, is basically if both of these are greater than 1, then we return -1, because we won't be able to move to those locations. Now we keep a visited vector bool of type bool, in which we will be storing or tracking basically the nodes or the cells that we have visited, not nodes. And in this we use a priority queue, which is basically going to be a minimum heap. So it will order it by, not a minimum heap, but it will order by min time to reach each cell, and we'll follow the Dijkstra's algorithm. So this is basically initializing the priority queue, which will store the time, row, and the column, and then we push initial our this value, which is grid of 0 comma 0, right? And the coordinates x and y. So this is x and this is y. Now the standard procedure that we follow in Dijkstra's algorithm, while the priority queue is not empty, current is equal to pq.top, pq.pop. Then we take the three values, time, x and y. First we check in case we have reached the bottom cell, that is n minus 1, n minus 1. Grid of n minus 1, n minus 1 is the bottom right cell. If we have reached here, that means we can return the time, and that is when our algorithm ends. Now we skip if the cell is already visited, so we check for each x and y. In case the cell is already marked in the visited, then we can continue, we skip it, and we have to basically, when we're moving to any cell, then we also need to mark it as visited. So once we move here, we have to mark this as visited. So we set visit x5 is equal to 2. Now basically the directions I have here, so these are basically directions of 1 comma 0 would mean we go 1 in the horizontal direction and 0 in the vertical direction, that means right. This is right. Then -1 would be in towards the left. Then this is up 0 comma 1, where we go 1 in the vertical but 0 in horizontal, and down is basically 0 comma -1, where we go 0 in horizontal, but on the x-axis we go -1 unit downwards. So these are the directions that I stored in a vector of in a matrix, right? Now so we traverse all the basically the all the 4 directions we traverse for this and store the next row and the next column. So this is how we get it, and we check if it is valid. So we need to also make sure that whether it is inbounds or not. So for that we check if our I greater than equal to 0 and I less than n, that is inbounds of the for the horizontal part, and j greater than equal to 0 and j less than n for the vertical movement part. We return true, this is valid. In case it is not valid, it would return false. So in case it is returning false, that means we are going out of bounds. So this case is of out of bounds, right? So we continue then. Otherwise, we calculate the wait time required to move to next cell. So as I explained to you that basically we have to calculate the wait time. In case the next cell, this for example here, was not available at time t is equal to 4, because the value should be less than or equal to the grid of x comma y. So we can move back, waste time, and get back here. So the solution here is that we check in case the value is coming out to be even, the grid value minus the time, the current time. If it is even, then we set wait time as 1, otherwise the wait time is 0, right? Now this logic I'll explain in a couple of seconds, but firstly we get next time, which is int of next time would be max of the grid plus the wait time and time plus 1. So we have to get the maximum here, and then we finally push the next row and next column and also the next time. And in case we are not reaching here, we will get here, which means we will return -1, that is it is not possible to reach it. Now I'll show you the logic behind it. So basically, if we have the top left corner and all neighboring cells have a minimum time greater than 1, we are stuck. There are no other accessible cells to waste time on, and thus the solution is not possible, right? Before that, let me show you the logic for even and odd. So when we are stuck in a cell, unable to move forward because all neighboring cells are inaccessible, the higher minimum times with higher minimum times, right? So in this situation, we can waste time. So we can wander around to previous cells. We can move back and forth between current cell and any previously accessible cells till the neighboring cell becomes accessible. That is when the time becomes greater than the grid value, right? So the time we need to waste is determined by the difference between the current cell's time and the minimum time of an accessible neighboring cell. So it's important to note that each unit of time wasted takes 2 seconds since we travel to a previous cell and return to the current cell. Therefore, if the difference between current time and the target cell's time is odd, we can step into the target cell exactly when it becomes accessible, right? And in case the difference is even, we arrive the target cell 1 second after it is opened. That is why here, for the even case, I have set the wait time as 1, since it would happen 1 second after it is opened. But for the odd case, it would step into the target cell exactly when it becomes accessible. That is why wait time is equal to 0. So you can also go through this demonstration, right? And we have basically applied Dijkstra's shortest path algorithm, and this is the whole algorithm. You can go through it. This is the whole algorithm that I've implemented, and I'll just it's accepted or not. And yeah, it has been accepted.